Welcome to 51st lecture of Digital Electronics subject related to electrical engineering syllabus. So, in this lecture we will be dealing with full subtractor, introduction to full subtractor and realization of full subtractor using XOR gates as well as AOI logic. In the next lecture we will be going with the realization of full subtractor using NAND gates only, and in lecture number 53 we will be going with realization of full subtractor using NOR gates only. So that is planned for lecture number 51, lecture number 52 as well as lecture number 53. Now coming to before going into full subtractor, some basics needs to be brushed out. So coming into full subtractor. Full subtractor is basically a 3-bit subtractor. This is basically a 3-bit subtractor. Here what happens is that for some reason, for some example, I will show some examples. 0 minus 0 minus 0. 0 minus 0 is 0, minus 0 you will get 0. 0 minus 0 minus 1. So here what we get? So 0 minus 0 is 0, that 0 minus 0 is, so this is difference, this is borrow, you can take like that. 0 minus 0 minus 1. So here difference is 1, that is again with a borrow 1. Again, if you are having 0 minus 1 minus 1, what is it? 0 minus, what is 0 minus 1? 0 minus 1 is 1 with a borrow 1. Okay. That should be again subtracted from 1. So what happens? The difference becomes 0 and borrow remains there. So it is 0 and borrow is 1. It is 0 minus 1 minus 1. Difference is 0 and borrow is 1. That is how the split is like this. If it is 0 minus 1, 0 minus 1 is difference is 1 and borrow is 1. And that is again subtracted by 1. So what happens is that difference becomes 0. That is 1 minus 1 becomes 0. But borrow is remaining it as 1. Again, if it is 1 minus 0 minus 0, difference is 1 and borrow is 0. Again, some other examples, if it is 1 minus 1 minus 1, what is it? 1 minus 1 is 0, then 0 minus 1 is 1 with a borrow 1. So these are some examples of 3-bit subtractor, and we will go with the truth table in the next slide. Okay. So this is basically a 3-bit subtractor, and the inputs to the full subtractor. Inputs to the full subtractor are A, first bit A, B and borrow in. A, B and B n. If you are drawing the block diagram of a full subtractor, it will be A, B and Bn. Similar to seen in our fuller, here we have Bn. This is difference, that is D, and borrow. Borrow is P. So this is a general block diagram of a full subtractor. So now let me draw the truth table and from the minterm and maxterm expressions of full subtractor. Truth table of full subtractor. Okay. Here we are having 3 inputs. Inputs, outputs. So the 3 inputs are A, B and D. Sorry, it is B in. This B in. Outputs are difference and borrow. 1, 2, 3, 4. 1, 2, 3, 4. 0, 0, 1, 1. 0, 0, 1, 1. 0, 1, 0, 1, 0, 1, 0, 1. 0 minus 0 minus 0. Difference is 0, borrow is 0. 0 minus 0 minus 1. Difference is 1 with a borrow 1. 0 minus 1 minus 0. That means 0 minus 1 is 1 with a borrow 1. And sorry, just with a borrow 1 only. Yeah. So borrow 1. Yeah. Now 0 minus 1 is 1 with a borrow 1, and that 1 minus 1 is again 0, that borrow remains as 1. 1 minus 0 is 1 with the borrow 0. 1 minus 0 minus 1, that is 0 with the borrow 0. 1 minus 1 is 0 with the borrow 0. 1 minus 1 minus 1. 1 minus 1 is 0 and 0 minus 1. 0 minus 1 is 0 minus 1 is 1 with a borrow 1. Now if you are writing the corresponding decimal equivalents, corresponding to A, B, B in scene 0, 1, 2, 3, 4, 5, 6 and 7. And if you are writing the min term expression, for difference, so you will get 1, 2, 4, 7. Difference is sigma m 1, 2, 4, 7, and borrow is sigma m 1, 2, 3 and 7. Sigma m 1, 2, 3 and 7. Now to write the match term expression, to write the match term expressions, I will go with another color. Okay. Difference, what will I get? Pi m with 0, 3, 5, 6. Pi m 0, 3, 5, 6. And borrow, you will get it as pi m, pi capital M, 0, 4, 5, 6. 0, 4, 5 and 6. Now you got the min term and match term expressions of this full subtractor. Now let me come to detailing about this full subtractor. Okay. So here I am having what? Okay. Coming into the expressions of full subtractor. Okay. So difference is given by 1247, that is sigma m 1247, sigma m 1247 is equal to, you can write as AB B in, or AB B in, or AB B in, or AB B in. 1 is 001, 2 is 010, 010, 4 is 100, 7 is 111. Okay. Now coming into borrow. Borrow is sigma m. Borrow is sigma m 1237. 1, 2, 3, 7. And thus A bar B bar B in, or A bar B B in bar, or 3 is 1 1. So that is A bar B B in, or A B B in. So you've got the expressions for difference and borrow. Now let me try to draw. Okay. Now if you are taking this B in and B in bar. Okay. Now this is expression number 1. This is expression number 2. Now in expression number 1, from first term and last term, B in is common, and from second term and third term, B in bar is common. Therefore we can write difference as B in and A bar B bar or AB, A bar B bar or AB, or B in bar and A bar B or AB bar. So what is it basically? That is B in and A XNOR B, or B in bar and A XOR B. I am taking A XOR B as H. Therefore we can write it as B in H bar or B in bar H. So what is it basically? That is B in H or H. What is H? That is A H or B. So that is that you can write as B in H or A H or B. What is it basically? That you can write as A H or B H or B. So that is the difference. So here we will take into account B in H bar or B in bar H for realization using NAND gate as well as NOR gate. Okay. Now coming into this one, borrow. In borrow, what we can take? Coming into borrow, which all elements we can take? B in bar, B in. So A bar B is common in first two terms. Sorry, second and third term. A bar B is common, and the last two terms, which is common, B in is common. Therefore, we can write borrow as B in and A bar B bar or AB or A bar B and B in or B in bar. Right? What is B in or B in bar? B in or B in bar is 1. And what is this? This is B in and A H nor B or A bar B. What is it basically? That is basically B in H bar or A bar B. Right? B in H bar or A bar B. So that is expression for B, and for B we will try to use this expression. This one. Try to use B in H bar or A bar B. Okay. So now coming into realization of full subtractor. Realization of full subtractor using XOR gates and give it AI logic. Okay. So coming into first difference. What is difference? Difference is A XOR B XOR B in. This we can write it as H XOR B in, where H is equal to A XOR B. And what is borrow? Borrow is B in H bar or A bar B. Borrow is B in H bar or B in H bar or A bar B or A bar B. So first we will realize X. What is X? X is A, B. If you are XORing that two, and this XOR, you will get X. So this is A XOR B. That is X. Now difference is H XOR B in. So B in is here. That is again XOR. So that gives borrow. Sorry, that gives the difference. Difference is what? That is A XOR B XOR B in. That is you will get the difference. Now what is borrow? Borrow is B in H bar. B in is there, H is there. So you take H bar. So how do you take H bar? Take a NOT gate. B in H bar. This is B in H bar or A bar B. So A is there, B bar is there, B is there. Yeah. You NOT gate to A. So this is A bar B, and you OR that two. You OR that two. So here what we get? So here you will get the borrow. Okay. So here you can see that if you are looking to half subtractor, this much forms these three. But we are looking to half subtractor circuit. Let me check the half subtractor. There is a basic half subtractor. Yeah. So this is the basic half subtractor. Okay, having one XOR gate, one NOT gate, and one AND gate. Okay, that is a basic half subtractor circuit. And if you are going for this full subtractor circuit, the same thing you can realize it here. Okay, that is, if you are looking like this much forms a half subtractor. And one more thing, this one. So taking this part like this. Okay, that forms another half subtractor. Okay, that means you can say that full subtractor is a combination of two half subtractors. So this is realization using XOR gate. Next one is realization using AI logic. Realization using AND or invert logic. Realization using AND or invert logic. So again I will write D is equal to A XOR B XOR B in. So what is it? That is X XOR B in. What is it? That is X B in bar or X bar B in, where X is equal to A B bar or A bar B. X is equal to A B bar or A bar B. Okay. Now what is borrow? Borrow I can take as borrow B in X bar or A bar B. B in X bar or A bar B. So first you realize X. So X is what we are having two inputs, A, B. A, B bar. B bar is there. So you are having this is A, B bar. Next one is A bar B. So this is B. You are ANDing it, you will get A bar B, and you OR it, or that too. If you are ORing that too, you will get X. Now coming to next one, difference. Difference is X B in bar. I am having B in. Take B in bar. And get this is X B in bar. Next one is X bar B in. So this is X bar. You take B in. You AND it. This is X bar B in. Okay. And if you are ORing that too, you will get the difference. Now what is borrow? Borrow is B in X bar. Okay. So here you are getting B in X bar. B in X bar is there, or A bar B. A bar B is here. Okay. You OR that too. Okay. So that is borrow. Now if you are looking into this circuit, again you can see that this much. Yeah. AB, yeah. So if you are going to this much, that much forms one half subtractor. And coming to the next part, this part forms another half subtractor. So what we can say is that full subtractor is basically a combination of two half subtractors. So with that I am ending with the lecture, an introductory lecture of this full subtractor. So to recap, what is a full subtractor? It is basically a 3-bit subtractor. It is having 3 inputs, A, B and borrow in, and the outputs are difference and borrow. Now coming into this one, the truth table. The truth table is formed and the corresponding min-term and match-term expressions are derived. And from there the expression of full array is derived. Full subtractor is derived. Where difference is, you will get it as the difference is A XOR B XOR B in, and borrow is obtained as B in H bar or A bar B, where H is equal to A XOR B. Then realization of this full subtractor using XOR gates is done, as well as realization of this full subtractor using AY logic is done. So from these two circuits, it is clear that full subtractor is basically a combination of two half subtractors. So with that I am ending with this lecture, and in next lecture, that is lecture number 52, we will deal with realization of full subtractor using NAND gates only. Thank you.